IMSC has this nice setup. Like people can record talks in IMSC, So like I see your lectures in like YouTube channel, which is nice, very nice.
Yes, we have a media room. So previously, before COVID stuck, that's where people used to record if they wanted video tape lectures. Most of them were held there. Sometimes there has been lectures which were recorded in the classroom, in classrooms also. But then because the classrooms are big, they'll pass around microphone. I mean, there's a bit more because the media room is smaller and a little more compact. And so, I mean, that's custom built for that only. But then we all started after COVID. We all became media people. We all started recording our own talks and so on. So I guess that probably the significance of the media team is emphasized in situations like this. Because faculty members to teach, we are given licenses, Zoom licenses to teach, but a lot of these things broadcasting over YouTube channel and so on, only they can do.
It's nice.
Media team would be great. For example, if you see this YouTube channel with 3 blue, 1 brown, the videos that he makes, I mean, they are really well made. And for NPTEL or other kind of courses, we have videos, but they're not that professional. It's just normal teaching video. If there is a proper media team and proper video animation team, then the quality of talks and quality of
course, exactly. That.
Hi, Aritra. I think Aritra also is here.
Hi, Aritra.
Switch on the camera. What is happening? Did not take shower today or something?
I the camera. I have told this to keep their videos, some of them.
Yeah.
I miss that coffee Aritra drinks. It's like fancy one.
You can come here anytime. We'll organize something in nicer, then all of you come here and enjoy some good coffee.
Chocolates and coffee.
Yeah. So Arjit has his own experience with this NPTEL guys.
Oh my God! I met such a ruckus with I think they hate me now.
It was the doctors really. Actually, they recorded one of the workshops that we are organizing, and Arjit was one of the speakers. And at the last moment, they told that you have to present using the stylus, and but it went well. Nice.
Yeah, it was okay.
Or shall we start?
Let's say I just introduce like in 20 seconds at 10 o'clock, and then I will start exactly at 10. Okay, so today our first speaker is Arindam Khan, who is a faculty member at IISc Bangalore. He will be continuing his talk on approximation algorithm for maximum independent set of rectangles. Thank you, Arindam.
Thank you, Arjita. And welcome everyone for today's talk. So yesterday we talked about some basic notions and definitions related to maximum independence of rectangles, and we started talking about the approximation algorithm, but today it will be more technical, and we'll go deep into the algorithm. But in the first 5 minutes, let me recapitulate what we did yesterday, and then we'll start. So yesterday we talked about first definition of approximation algorithm, and then we talked about pitas, e-pitas, f-pitas, q-pitas, etc. So if you, so I'll just go over quickly, but if you need any point to stop me, I can stop and explain if something is not clear, what I did yesterday. And then we talked about rectangles and packing problems, why they're cool, and then talked about independent set problem, then talked about geometric intersection graph, and talked about the algorithm for independent set of rectangles, maximum weighted independent set of intervals. And there we talked about a dynamic program algorithm, and we told that our algorithm will be a generalization of this idea only. And finally, this is the problem which we study. We are studying that we're given a set of n axis parallel input rectangles, and the goal is to find a set of non-overlapping rectangles of maximum cardinality. So in this example, this is a set of maximum cardinality non-overlapping rectangle. So you have both geometric viewpoint where you have non-overlapping rectangles, and with a graphical viewpoint where if you create the geometric intersection graph of rectangles where there is an edge between two nodes if the objects overlap, and if you find the independent set in that particular graph, it's also giving you this non-overlapping set of rectangles. And then we showed why it's theoretically important, connections with several other problems, and the present state of approximability. And as we mentioned, the previous base was 10 approximation, and the goal was to get an improved approximation guarantee with better runtime and simpler analysis. So this was the slide which I talked. I spent some time yesterday, but let me go over this again. So what we are giving is we are giving a 2 plus epsilon approximation, and the idea is as follows: that there are too many number of candidate independent sets, exponential in number. So what we're looking for some kind of structured solution. So yesterday we talked about guillotine cuts. So guillotine separable solution will show it to be a structured solution. And one can show you can find the best guillotine separable solution in polynomial text. So the size of the space of all best guillotine separable solution, that's only a polynomial size subset. And then what we'll show that if there's a good if we can show any guillotine separable set, any independent set, if I take, there's a good guillotine separable set which is within a small factor from the independent set, then using that property, we can actually find that solution by a DP, and that will return us some solution with some approximation guarantee. So we'll go over this idea in detail today, but that's a high level thing that we're doing, that we have a lot of candidate solution. We want to create some kind of structured space which we can find efficiently, which structure efficiently in polynomial time. And these structured solutions are good approximation of the original set of candidate solutions. And then also this is kind of the best that you can achieve, because presently even for line segment, axis parallel line segment, 2 approximation is best known and nothing is better. Nothing is known which is better than 2. This is the status. And then we talked about guillotine cuts yesterday. And guillotine cuts are end-to-end cut, which divides a piece into 2 rectangular pieces, and that creates some kind of a tree structure like this. We saw that we start with some object, some rectangular piece, and then we cut, and then you would get 2 pieces, and then again we cut and continue. So you're getting a binary tree, and at the end, each leaf contains exactly 1 rectangle. And the question was whether you can extract all rectangles. So a rectangle is not killed if it is finally, it belongs to some kind of a leaf node, and it does not intersect any of the guillotine cuts. So the question was, can you always separate out all the rectangles by guillotine cuts? The answer was no. But can you separate constant fraction of the rectangles? And that was a conjecture, but the best bound we know is there are some examples where you cannot separate out more than n by 2 rectangles. So half fraction you have to lose. But on the algorithmic side, the best we know is n by log n plus 1. So there's a huge gap. And then we talked about the algorithm, how you get this n by log n plus 1 rectangles. Basically, you create log n number of poles, and you show each of, and you divide the set of rectangles into these log n classes, and you can show each of these classes you can separate using guillotine cuts. So if you take the highest weight class from them, you will already get n by log n plus 1 rectangles. So this was a state where we stopped. So now let me continue. But any question regarding previous like yesterday's talk? Okay. So now we'll talk about the connection between guillotine cuts and MISR. So when we talk about MISR, we are given a set of rectangles which are overlapping. Whereas in guillotine cuts, we're talking about set of rectangles which are non-overlapping. So think of a MISR instance, which might be something like maybe something like this. Whereas for the guillotine separable instance, the object are something like this, which is non-overlapping. So how do we connect these two problems? So first, let's say we have this existential property that if I have any embedding of n non-overlapping rectangles, then there are n by alpha fraction of rectangles which can be separated by guillotine cuts. So it's an existential property. I don't need an algorithm, just some property, even if it takes exponential time, that's fine. Now assume the optimal MISR solution is opt. So maybe this is the MISR solution that I have. MISR instance, and this is the solution, opt of MISR. Now, as you see, the optimal solution of MISR is a set of non-overlapping rectangles, but they may not be guillotine separable. But the conjecture, the property P1, it ensures that if it is true, then opt may not be guillotine separable. But if I start with the optimal solution, that is non-overlapping, so at least opt by alpha number of rectangles will be guillotine separable. And then we'll show that actually there is a dynamic program which returns the optimal guillotine separable set for a MISR instance in order n to the power 5 time. And okay, there is a question. Why is the guillotine cut problem only defined for non-overlapping rectangles? No, actually it is defined for general objects also. So there is you can define it for convex object, you can have axis parallel cut, non-axis parallel cut, all. So it is studied. So there is a classical paper by Park and Tardos called Cutting Glasses. In that paper, they study a lot of different types of objects. But in this case, we are studying about independent rectangles. So the connecting problem becomes this Park Tardos problem for rectangles. And also for other objects like squares or disk, etc., this Park Tardos conjecture is kind of settled. We know we can separate constant fraction of rectangles. But for these rectangles, it's not known. There's a huge gap between 2 and log n plus 1. Yeah, so what we'll show later that there's a dynamic program which will return the optimal guillotine separable set in order n to the power 5 times. So it's a polynomial time algorithm. So then the solution that we're returning R prime, that is at least more than opt by alpha, because already opt by alpha was a guillotine separable set. So that in turn give you this alpha approximation algorithm for MISR. So this was the optimal solution, but maybe, so this already shows there is a guillotine separable set which is like this, 3. But maybe there's another solution which looks like, I don't know, this, which is also guillotine separable, and it will return this solution. Fine. So this is the connection between guillotine and MISR. If we have this existential property that there is a good guillotine separable solution, we can find it efficiently. And that could be a good proxy for the optimal solution of MISR. So is this connection clear? Any question about this connection? Because we'll build on this connection. And the point to notice here is existential. I don't need really algorithmic property here, because this algorithm will return actually the best guillotine separable solution. So that is ensured. So I just need a structural property that actually they are close enough. Guillotine separable solutions are good approximation of MISR solution. Okay, so let me tell you what is the DP, and the DP is basically the same as, I mean, the kind of extension of the previous DP that we studied yesterday for weighted intervals. So we can assume that all the rectangles have some integral coordinates in 0 to 2n minus 1. You can just extend both sides of the rectangles, and there are n rectangles, 2n endpoints. You will get 2n cross 2n grid, but this is non-uniform grid. But you can stretch it and make it a uniform grid, and then all the rectangles have coordinates in 0, 1 up to 2n minus 1. And then what we do is we create this DP, and in the DP is a table. So DPC stores the optimal guillotine separable set for MISR for a rectangular region C. So in the beginning, C is the whole square. And the base case is if C coincides with the rectangle, we give that to be the solution. So in this case, if this rectangle coincides, this region, red region coincides with the rectangle, we return that to be the solution. And if it contains no rectangle like this, we return empty set as the solution. That's a simple base case. And for the recursion, what we do, the recurrence relationship is you divide this C into by a guillotine cut into two sets C1 and C2, and there are many guillotine cuts. So one is this, maybe other one is this, and so on. But number of possible such guillotine cuts is only 2n, because if you see, we only have a different structure when some rectangle ends or begins, and there are only 2n possible endpoints of rectangles. So there are 2n possible cuts that we have to deal with. And then for each of these cuts, let's say this is the cut, then I delete this rectangle because it's intersected by the cut, and also this and this. And then I recursively solve C1, this part, and C2, this part. And I do it for all possible such cuts, like 2n possible cuts on vertical side and 2n possible cuts also horizontal side. You can also consider those cuts and return the best one. So DPC is DPC1 union DPC2, where the cardinality of DPC1 plus DPC2 is maximum among all partitions of C1 union C2. All partitions of C1 and C2 of C. So what is the size of this table? As I said, there are 4n possible cuts only, order n possible cuts. How many DP cells are there? So DP cells are also defined by the endpoints of rectangles, because that is the interesting point. So each of the, this is rectangular region. So each of these sides have 2n possible choices. So 2n, 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 n to the power 4, order n to the power 4 possible choices. The number of DP cells is order n to the power 4, and that gives you n to the power 5 algorithm. So is this part clear? Why this DP works? It's just similar to what we did yesterday. The only difference, so there was order n possible cuts in the interval case. Here also it's the same. There we looked into the interval, and the interval had order n square possible choices. Now we have rectangular region, so it has n to the power 4 possible choices. Okay.
So why it is n to the power 4?
Yeah. So as I mentioned, this DP cell C, C is a rectangular region. So let's say, so when we are going bottom up, let's say, so there is a rectangular region C that we want to compute. Now, how many possible choices of C can be there? So this top side, it can have 2n possible coordinates, because as I mentioned, there are in rectangle, there are 2n possible endpoints. So only those places are interesting for any region. Other regions are kind of, will have same kind of structure. So this 2n number of possible top endpoints, 2n number of possible bottom endpoints, 2n right endpoints, and 2n left endpoints. Total, you have 2n to the power 4 possible choices, which is order n. So that's a crucial point. I mean, if we have 4 sides, you see here we have 2n to the power 4 possible choices. If we have the cell with, let's say, t number of axis parallel segment, let's say instead of square, I have something like this kind of an object which has t sides. Then instead of 4, it will become t. And similarly, if I have different types of cuts, instead of straight line cut, if I have some cut like this, then that will have again 2n choices, 2n choices, 2n choices. So instead of order n possible cuts, you will have n to the power 3 possible cuts. But for this example, as we have only guillotine cuts, which is straight line cut, we have only order n possible cuts. And if you're as we are only considering rectangles, we have only order n to the power 4 DP cells. So in total, this is giving us n to the power 5 algorithm. Okay.
So just to just to check. So I mean, so this really extends to the case we have 3 dimensions rather than 2 dimensions, right? And it also works in the weighted case, same thing.
Yeah, this actually works for the weighted case as well, and you can extend it to multiple other dimensions as well. But the runtime would be more because it will become hyperplane instead of straight line.
Right. Yeah. Okay. Thanks.
That will work.
Hello. Instead of this vertical line, while you are sort of taking this orthogonal line, if in that case, is the number of DP cell reduces, or this is DP cells, like if you are sort of taking the vertical line, then it is sort of n to the power 4 because of these 2n on each side. And now, while you are sort of going for this this orthogonal sweep line sort of thing, so in that case, is this number of DP cell reduces or it remains the same?
Number of DP cells increases because I'll actually talk about that in the next slide, because the DP cell depends on the number of sides. Now, if I take this kind of a cut, then the DP cell will have this complicated kind of shape, which don't have 4 sides, but it has more and more sides. So if you have more sides, then the complexity of DP cell will increase. I will talk about this in the next slide, but this is the first. Just let's think about the Guillotine case and understand why it's n to the power 5. If that is true, then we can go to the next step when we'll talk about more complicated polygons and more complicated cuts. But is this part fine, n to the power 5 part?
Yes. Thank you.
Fine. So now we'll go for the more complicated objects. Now the question is, we know that Guillotine separability, this alpha factor is at least 2, but the based on bound is log n plus 1, and we don't know how to improve it. So the question is, as you see in this case, we have this binary tree, and when we cut by Guillotine cuts, we get 4 sides again, and we continue and so on. So can we generalize this? So one idea is, instead of this binary tree, we can go for k-array tree. We can have more partitions, and instead of rectangular region, we can probably have complicated orthogonal polygons. And as you see, the DP idea that we mentioned, that actually can be extended to this setting as long as both k and t are integers. So the reason we are going for this is, if we look at Guillotine cuts, that kind of restrictive. For example, the example that we talked about, this 4 rectangles. If I have Guillotine cuts, you cannot separate out all the rectangles. But if I give you some more flexibility, that I can actually cut something like this and then bend like this and then like this, then actually you're not cutting any rectangle. So you can actually bypass some rectangle along its boundary and then go. So allowing more complicated cuts is beneficial. Then probably you will get more. And second option is, instead of having only 2 cuts, maybe you can have more complicated cuts. So think of maybe the starting object was something like this, and then I can have this red cut, which divides the object into 1, 2, 3, 4, 5 region. So as long as all these smaller objects have bounded complexity, let's say 10 sides or 20 sides, some constant number of sides, and the cuts also have, the number of region that you get is also constant, I claim the DP will work, and I'll still get the best such separable sets in polynomial time. And that is the idea based on which we'll go. And we'll show first a 6 approximation, for which we'll use a tripartition, and the number of sides will be around 26. And building on that, we'll show a 2 plus epsilon approximation, where we have k is equal to actually 2 and t equal to something. Let me talk about the DP table now. So why it is true. Now we're talking about some k-array partition into t-sided polygons. Think of the
can everyone please switch off their
there is some noise. Suvendu Saha, I think you have to mute yourself.
I'm trying to mute.
Anyway, so so why this DP table works when you have k-array partition into t-sided polygons. This is one example. So let's say some complicated polygon is there that we are dealing with, which has t sides, and now we can show if we can show that there is a partition of this object into 3 regions by this yellow cut, and let's say this yellow cut has it divides into 3 regions, and it could be even k actually. So in this case, k equal to 3. So C1 is one region, C2 is other region, and CK is another region. So there are 3 regions, and each of these regions has at most t sides. Then why this DP works? Because then again, for the DP cell, we look at how many possible candidate polygons are there. We are looking for only polygons which has t sides, and each of these sides can have 2n possible candidates. There are, if it has t possible sides, there are t by 2 vertical and t by 2 horizontal sides, and each of these vertical sides have 2n number of possible candidates. Horizontal sides have 2n number of possible candidates. So total number of possible orthogonal polygons which has t number of sides is 2n to the power t. So in the last case, when we have t equal to 4, then it was 2n to the power 4 or order n to the power 4 for the guillotine setting. And if we have k-array partition, so there are k regions that you're getting, then this complicated cut, what is the complexity of this cut? So as we know, there are k regions, the total number of sides of all these k regions is at most kt, but each of these cut edge is shared by at least 2 of these regions. So kt by 2 is the complexity of the cut. So in the guillotine setting, it was only one cut like this, or other cut was like this. So there were 2n possible choices, 2n plus 2n, 4n possible choices. But now for this complicated cut, it has kt by 2 possible sides. So you can have n to the power kt by 2, 2n to the power kt by 2 possible cuts. And then the DP will work as the previous case. So what you'll do is you'll start with an initial object, and then you try out all possible cuts of size kt by 2. By size, I mean the number of sides in the cut is kt by 2, which divides the polygon into a k number of regions, and then you recursively call this DP process in the smaller cells and continue. And as long as k and t are constant, this DP will still run in polynomial time.
Don't you need to show something about smaller regions as well? I mean, if they are very high complexity, then you may not be able to.
Right. So that's what we have to ensure. The smaller regions, the complexity does not grow up. So for example, I want to maintain always the size, this complexity of the region remains t. That's one of the challenges. So for example, I can probably give, So for example, I can give you one example. So let's say I allow not guillotine cuts, but let's say some kind of L kind of cuts. So one kind of problem can happen is, let's say I start with this object, and then I cut like this L. Then the next object I cut like this L, and then I cut like this L and this L and continue. In that case, this region, its complexity increases. It may not remain constant. If you have this L kind of cuts many times, order n times, then the complexity of the region will become order n. By complexity, I mean number of sides of this region, because now it is 1, 2, 3, 4, and it goes on like this. It becomes too complicated. So we have to ensure the property that we start with the optimal some region, and then we divide into the smaller polygons, but we still maintain the complexity of the regions don't grow. So it will still remain, let's say, 26. That is the challenging part. We have to find such a partition. Otherwise, it will not work. And in guillotine case, it was very simple because you will never increase the complexity. It's just end-to-end cut. So it always remains 4. But when you have bends, it can increase. So we have to ensure to find some way, some kind of possible cuts, which does not increase the complexity of the region, the number of sides in the region. That's one of the crucial points that we have to ensure.
Okay, thanks.
Any question? There is some question on this. Is the claim that every small part is of size kt by 2? No. So my claim is every small part has side length at most t. Kt by 2 I am claiming is the complexity of this cut. So let me use some other color. So this, I am saying that, okay, the C1 region is this region, and this region, it has at most t number of sides. Similarly, C2 has t number of sides. C3 has t number of sides. And if I look at the cut, which is, let's say, this yellow region, this cut, total number of sides that we have in the cut is kt by 2. And that is coming from the fact there are k regions, each has t number of sides. Total number of sides can be kt. And the cut, for each of these edges, it is shared by 2 of the regions. So you can have at most kt by 2 number of sides. It can be actually less than this value, but a rough estimate is fine. The main point is, as long as k and t are constant, this remains constant, this kt by 2. So assuming this property is true, that I ensure some cutting strategy such that all these smaller polygons remain constant complexity. So number of sides of the smaller polygons remains, let's say, 26 or 1000, some constant value. and I ensure that the cut also has constant complexity. It has, let's say, 20 number of sides. Then I want to claim the DP will work. So is that fine? Is that claim, or any question regarding that? Because the number of DP cells, it only depends on the number of sides in these smaller regions, and they are constant, so it's n to the power constant, n to the power t. And the number of regions that we have k, it ensures it's constant, so it ensures the number of edges in the cut is also constant, and that ensures the number of possible choices that you have to iterate over in each of these DP step is also constant. So totally you have n to the power constant possible choices, and that gives you a polynomial size DP. So does the cut always have to be monotone? Yeah, that's a good question. Actually, for our algorithm, the fixed approximation it is monotone, but we can show for the 2+ epsilon it's not required to be monotone. So by monotone it means the cut can be it may not be something like it may not be something like this always, but it can be some weird shape like this as well. So that we'll go over. But for now, assume that this property is true, then the DP will find it. So then the next question is, how do we ensure this property? How do we ensure that the cut, we can always define cut such that the complexity does not increase? And then how do we ensure that, okay, even if it is true, what is the guarantee that we don't cut too many rectangles? So those two are more crucial part. But for now, I think this is kind of simple to understand that if we have this property, that there is some sequence of cutting, recursive subdivision or cutting such that each of these regions have constant complexity and there are constant number of regions, then the DP will find it. That's the thing you can assume for now. Okay. Fine. So now let's look at the recursive partitioning. And as I mentioned, that from the previous previous algorithm, what we showed is if we have k and t to be constant, number of partitions and number of sides in per region is constant, then DP will find it. But question is, how do we find such partition? And there were two ideas here. First, we show the cutting strategy, which uses something called fence and cutting. And then you have to show the analysis, that why it is ensuring that not many rectangles are cut by this, and that will be using some nesting and token counting argument. Okay, so to show this first part, that there is some cutting strategy, first we'll assume that the optimal solution that we consider, it is maximal. So maybe this is the optimal solution, but then we can enlarge it a bit. So grow such that the new rectangles are kind of larger or a superset of the previous rectangle. And we only work on the separability of these rectangles. And if we know that there is a cutting sequence which separates a good fraction of rectangles of this type, as these rectangles are superset, it also separates out a good fraction of rectangles of the optimal set as well. So from now on, we will assume the optimal solution looks like this. It's a maximal solution. So from now on, we'll assume that we are given, let's say, the maximal optimal solution, and then we'll try to process this solution and show there is a good quality solution which has this recursive partitioning property. Because then the DP will solve. So this DP was the algorithm. That is the algorithm for our problem. Now this part is showing us existential property. So it need not be algorithm. It can be just constructed. Okay. So what is the strategy? So first of all, if I have this kind of a rectangular arrangement, and if we find some cut, if the cut is in the boundary, then it's kind of lost because you lose all the rectangles that are cut, but you don't really make any progress because you lost those rectangles and you did not really make progress. So divide and conquer kind of once you have two smaller regions which are kind of balanced, and then you make some progress. So maybe it's better to have cuts which are not near the boundary. So we want to block or protect the boundary rectangles using something called fence. So if some rectangles are touching boundary or close to boundary, we'll create these fences which basically lies on the top of the rectangles. So on left side, this red fences are there, and right side, there are blue fences which are there. And then, so basically, these fences are horizontal line segment that join boundary of a piece to the boundary of a rectangle without intersecting any rectangle. So you can think of a ray is being shooted here. So the ray shooting is done here, and then it is hitting this rectangle, and this is the fence that we get. So if it hits a rectangle, then you stop. And yeah, if your rectangle is having a fence on one of its sides, we call it it's protected, or it's a boundary rectangle. So these rectangles, these boundary rectangles, we'll try to protect. We'll not cut them, and then maybe we find some cut. So the goal is I don't want to cut through the fences. So this kind of cut is not allowed. Fences will not be touched. They are protected. These boundary rectangles. This is not allowed. It violates property 1. And I also ensure that the horizontal segments of cut do not intersect in rectangles. This kind of cuts is also violating because this horizontal part is intersecting rectangle. So we'll only look into this kind of a cut where the horizontal part is not intersecting any rectangle. It is going along the sides. Only the vertical part can intersect rectangles. Like this. So we cut like this, and then probably we got this boundary rectangles, and we create the fences. Then again, we got another cut and create fences, and we continue. But now in this region, we cannot really cut again because whatever way we cut, we have to cut a fence if we just create a vertical line. So what we'll do is we'll use bends now. So the bending might be done like here, and then you get this region, and again you use a bend and cut like this, that kind of cut, and you get this and continue. So that will be our strategy. So intuitively, the idea is I want to start a cut from a bend, from a fence. So this is a fence. This is also a fence. So I want to start a cut along a horizontal line, which is a fence. And I want to exit the polygon also along a horizontal line, which is a fence. And I want to go vertically between these two. That's a high level idea, and we'll show why it works. Okay. So the partition rule will be something like this. So we will have some fences, and from some fence, we'll select the fence in some according to some rule. We'll shoot a ray on top and bottom. And if it hits some other fence or other rectangle, other fence actually, or a protected rectangle, then we actually go along that particular line and we exit, and that will give us this region. So one region is this, other region is this, and third region is this. And the invariant we'll maintain is this pieces will maintain to be horizontally convex. That means that if I take any 2 points, let's say it looks like this, any 2 points, draw a horizontal line that will remain within the polygon. So it is not a convex polygon, but it's horizontally convex polygon, and will ensure that this polygon's complexity or number of sides is constant. Okay. So now let's go into more detail what's being done. So we define fences again more formally. So for each point on the boundary of the left vertical edge of a piece, we shoot a horizontal ray towards right till it hits a rectangle. So in this case, we are shooting the ray and it hits here, so we stop here. Here we shoot the ray and it hits here and stop here. So these are creating some fences. And whatever rectangle stop side is contained in the fence, we call it protected. So we will not cut those rectangles. That's our invariant we'll maintain. So in this case, this is protected, this is protected, this is protected, and so on, because their top side, one of the sides are completely contained within this fence. And similarly, we do fencing from right side as well, and there we shoot the ray to the left. Okay. Okay. So now let me prove this line partitioning lemma, which will ensure that we can find a cut such that the complexity does not go up. So in this case, we'll show, okay, there is given a horizontally convex polygon which has 26 sides. We can find a cut C, and C is this yellow region, basically that cut, which has at most 8 line segments, which is constant. The cut has constant complexity. C divides P into constant number of polygons, 3 number of polygons, and each with at most 26 sides, and each are actually horizontally convex again. So K equal to 3, and again P equal to 26, it remains. And the cut has special property. It has only one vertical segment, and that can intersect some rectangles. So maybe this particular region, there are some rectangles that are intersected, but none of these rectangles are protected. So if it has fence, we don't intersect it. Otherwise, we can intersect, that is fine. We have to kill some rectangles. Only this vertical line will kill some rectangles. And the horizontal line segments will not cut any rectangles. So L does not intersect any protected rectangle. So L does not cross any fence. This is the lemma that we'll prove. And that will kind of ensure the property that the constant complexity and K and T are constant. So you can actually find this kind of a cutting sequence using DP. But then we have to show it's also good. So the analysis will be showing that it does not cut too many rectangles. But for now, let me just prove this fact that this property is true. So what we do is we know that the P has at most 26 edges. That's the assumption we start with. So in the beginning, we have only 4 edges, but as we cut, things can the complexity can increase, but we'll ensure it will never go beyond 26. So if you have 26 number of edges, then there are at most 13 vertical edges. So there are V by 2 number of left vertical edges, which is, let's say in this case 7. As you see, E1, E2, E3, E4, E5, E6, E7. There are 7 vertical edges, left vertical edges. And we divide this into 3 regions, ET, E3, EB. And they're kind of equally balanced. The middle portion has like slightly more maybe. So these two are V by 6 floor, and this is V by 6 ceiling. So we got these 3 regions. And now from this EM region, we look at all possible fences that are getting out. So maybe the fences will look like this. There are many, many fences that are going out. We take the fence which has rightmost endpoint. So in this particular case, this F is the endpoint. F is the fence which has rightmost endpoint. And from this endpoint, we shoot a vertical ray to the top and bottom till it hits a protected rectangle. So RT or RB is hit. If it hits, then we take this bend and we exit along that fence. Because RT was a protected rectangle, it's already has a fence here. So we just go along this and exit. So this is the cut that we are getting. So from this, we go like this and then this. This is the cut we are getting. So we have to ensure these 4 properties that I mentioned. And in this particular case, the 3 properties are kind of easy to check. First is C has only 8 line segments. It has constant complexity. The cut has because we have one vertical segment, one edge here, F. Then the second one is here, 2, then 3, then 4, then 5, and here it is 6 and 7 and 8. So the cut is of constant complexity. That is fine. There is only one line segment that can intersect some rectangles. And that is also true because only this is the line segment which can intersect some rectangles, because this is just bypassing the rectangles, the fence, this is also a fence, and it's also a fence. So all the remaining 7 sides are fences. Only one side is a vertical line segment which can intersect some rectangles. So third property is also true. And as you see that that L by definition, what we're doing is we're shooting this ray till it hits some protected rectangle, and then we take this bend. So it does not intersect any protected rectangle. That's also true. L does not cross any fence. So first, third and fourth properties are true. Now the last property you have to ensure that the complexity also does not go up. So in this case, we have to ensure that this cut complexity remains 26. So the reason it will not grow, intuitively what we did was we divided this vertical sides into 3 regions, ET, EM, and EB. Now if we look at the longest, we look at the fence which has the rightmost endpoint, and then we shoot the ray to the top and bottom. So that ensure that you will not hit any fences from this red region, EM. You can hit fences from the top portion or the bottom portion, but at least you will not hit anything from EM side. So now what happens is when we create this new region, the complexity of this region C1, it has some new sites. So you're adding 1, 2, 3, 4, 5 new sites. But we have to ensure that actually in the beginning piece we have 26 sites. We have to remove some of the sites so that we can support this newly added sites. And that is made sure because if I look at C1, it is disjoint from this set EB. and we made sure EB has sufficient number of edges, like V by 3 number of edges or V by 6 number of edges. In this case, it is roughly 5. And also, if I look at C2, then again it is disjoint from this ET edges. And if I look at this C3, it is disjoint from EM number of edges, EM edges. So that is ensuring that, okay, by this cut, we are increasing the complexity because some new edges are being added, but also the region that we are getting, it is not having a lot of edges which was there originally in the piece. So we are also decreasing the complexity there, and that is making sure the complexity does not grow up. So for example, if I look at C1, this region, what is the number of sides it has? Initially, the whole region had V number of sides, but now I know that, okay, at least number of vertical sides was V, and at least I know this is deleted. V by 6 number of sides are no more there in C1 because they are not part of C1. So that is minus, and we're adding 2 new vertical sides. One is 2, other one is 4. So plus 2, and you can show this is actually less than 13. And 13 was the bound that we need. That is at most 26 sides, at most 13 number of vertical sides. Similarly, you can show it for other sides as well. So this ensures that you have constant complexity. Any question?
So in this picture, is it possible that the fence F continues until the right side boundary?
Yes, actually that is possible. So that's even better. So that's a guillotine cut. So fence will continue and
that's right. Okay, sure. Yeah.
So that in that case, yeah, there can be fences. If you have guillotine cuts, the fences can go from one boundary point to other boundary point, and that's actually better for us. So this is a more harder case because the fence is blocked. Okay, fine. So now we have this constant complexity part as well, and we know what is the cutting strategy. So final part, we have to show that actually this is good cutting strategy. We don't cut too many rectangles. So recursive partitioning look like this. So you start with some objects, and then you first cut like this, and then cut like this, and cut like this, and so on. Continue. Now we have to show that we don't need too many rectangles. So for each filled rectangle, you can actually save sufficient number of rectangles. And each filled rectangle that is not horizontally nested, okay, so we'll define something called nesting and use some kind of charging argument to ensure that. So let me define this nesting relationship, which will be useful for the analysis. So now we are only in the analysis part. The algorithm was DP, which we did. The cutting strategy, which is essential, we showed in the previous part. And now we only focus on the proof of the approximation guarantee. So first we define a rectangle is vertically nested or blue if its top or bottom edge is contained in the interior of some other edge or boundary edge. So for example, if I take this edge, its bottom edge is contained within the boundary edge. So we call it nested vertically. Similarly, if we take another edge, let's say this edge, its bottom edge is contained within some other rectangle's boundary edge, interior of some other rectangle. So in this case, it's a vertical nested rectangle. Similarly, we can define horizontal nested. This is a horizontal nested rectangle, or it is red. In this case, this particular edge is contained in the interior of some other edge of some other rectangle. Now, one observation is a rectangle cannot be both red and blue. So, and if it is not red or blue, we call it gray. So why? So let's say this is vertical nested, this is horizontal nested. As you see, if something is vertical nested, you have some extra space here. And if you have it horizontal nested as well, then you need some rectangle which is like this, and that cannot be true. So a rectangle is either vertically nested or horizontally nested, or it may not be nested at all, which is this kind of a gray rectangle, which is neither. So this is kind of a partition of the rectangle, and I will assume that the number of red rectangle is small, so less than half. And non-horizontal rectangle, nested rectangle, which is either blue or green, they are more than half. Now we define something called seeing, which we'll use basically for charging. So we call a rectangle sees another rectangle, sees the corner of another rectangle. So let's say R is a rectangle. It sees another rectangle R prime. R prime's corner, top left corner, let's say C. If we join this corner with by a horizontal line to this particular rectangle, and this does not intersect any rectangle in R, it does not contain top edge of any rectangle, and it is not the bottom right corner of rectangle rectangle R. Then we call it C. So for example, if I look at a particular corner point, then it is not visible, because if I join this corner point with this, then this is containing the top edge of another rectangle. This is not visible. So think of you are here and you're looking from this place, and you can only see horizontally. What is the first point that you hit? That is the rectangle that you can see. Similarly, this region also you cannot see, because if I join this and this, it is intersected by another rectangle. It's blocked by a rectangle. You cannot see. And third point is here. If I have here, it's kind of a below point. So if I look at any interior point of the rectangle R, it cannot see this point horizontally. So this is the definition of seeing. You can just assume that, okay, if from I take a rectangle, I take a rectangle, I take a corner, and if I join them, and if it does not intersect any rectangle, or it does not contain rectangle, can you mute yourself?
Excuse me, one second, Arindam, please mute yourself. Shubhendu, I think you need to mute yourself. Okay.
Okay. So that is the definition of C. Okay.
Excuse me, can everyone mute themselves except the speaker?
I'm not trying to mute him, but I'm not able to mute him also.
Anyway, so the point is, this definition of this seeing, it ensures that if I have some horizontally nested rectangle, the red rectangle, then it does not see any corner in the nested side, because the whole region in the right side is completely blocked by another rectangle. So red rectangles, we cannot really see any corners. But what will ensure, if a rectangle is vertically nested or gray, then it sees at least one corners on each side, and that will be helpful in the token distribution. We will actually distribute token of killed rectangle to the rectangles that it can see. Okay. So the seeing definition is clear. I mean, it's just saying that if I take a corner, I take a horizontal line joining the corner and the particular rectangle, it should be the first rectangle. There shouldn't be any rectangle in between them touching the particular line. Okay, so now the claim is, if some rectangle is not horizontally nested, it can see at least one corner on each side, or it is already protected. So I have 10 more minutes. So let's say what we do is we take one rectangle R and it is not horizontally nested. So what we'll do is we extend its top edge till it hits the boundary point. And if there is, it already hits boundary point, then it's already protected by definition of fence. So there should be some other rectangle which is blocking it. So this is the first such rectangle. Now there can be two cases. One case is that rectangle's y coordinate is same as R's y coordinate. The top edge kind of lies in the same vertical line, horizontal line. So in that case we are fine, because then this corner is seen by the rectangle and this corner is seen by the rectangle. Whether R prime has the bottom edge above or below R, both the cases we are fine. So let's take the other case when it is not the case that this is lying on the same horizontal line, but they can be above or above. Basically, this is blocked. This line is blocked by this rectangle. So then, first of all, we assume this is not horizontally nested. So this kind of a situation will not occur, that R is completely blocked by R prime, because it's not horizontally nested by definition. But then there can be two cases that, okay, this two rectangles R and R prime, they are touching each other or not. If they touch each other like this, we can show this corner is visible. And if they don't touch, then we can show using the property of maximality, that the only possible case which can happen is this case. But then again, we have one corner which it can see. So that's the high level idea. I will not go to the proof, but it's not too long either. But I have less time, so I will not go over the proof. But the point is, if it is not horizontally nested, it can see one corner on each side. So charging argument is this, that if some rectangle is not horizontally nested and intersected by L, then for the rectangle we have charge 1, we distribute half charge to the corner to the left and half to the right. So there are these two claims which will give you the 6 approximation proof. The first claim says that a rectangle R prime receives a charge to at least one of its corner. If it happens, then it is protected. So think of this case. This rectangle. So it is receiving some charge. Maybe this corner is receiving charge. Why is it receiving the charge? Because some rectangle was killed, and that rectangle could see this particular rectangle. And that's why this killed rectangle, let's call it 1, this is 2. So 1 was distributing half charge here and maybe half charge here. So this corner got charge from this. So as it got the charge, this was actually the first rectangle that was visible from the rectangle 1. So that's why it got the charge. So once we kill the rectangle 1, now we create this rectangle 2 is actually visible from the boundary, or it is becoming a part of this fence. And once you get a fence, it becomes protected. So if a rectangle gets a charge, it becomes protected. And that's what we want. So basically, we'll ensure that there are many rectangles which will receive the charge. And that means there are many rectangles which will be protected by fence. That is good for us. And then also we'll show that the corner of rectangles are not charged many times. So if a rectangle gets charged once, it will not, the same corner will not get charged anytime further. The reason is when we get the charge, we get the charge when some rectangle which was just next to it was cut, and this was the first rectangle which was visible from the fence, and it gets a charge. So the first time it gets there and then it gets protected. So next time onwards, it cannot get any charge because there is no more rectangles which can be there for which this property is true. So each corner will get charged at most once. And this gives you the 6 approximation. So this claim 2 and claim 3 we assume. And then the proof is, okay, first we lose a factor 2 because we remove all the horizontal nested rectangles, and only we consider the rectangles that are not horizontally nested. And we assume the number of horizontal nested rectangles at most half. So we lose at most a factor half. And now for the remaining rectangles, so basically we are cutting some non-horizontal nested rectangles and we are distributing the tokens of these rectangles. And what we showed is any rectangle is receiving, each of the corners is receiving at most once charge. There are 4 corners, so you'll receive 4 charges, and each of them has half token. So at most 2 amount of charge is received by each of these rectangles. And once they receive, they are protected. So if we have k number of not horizontal nested rectangles that are cut by vertical lines, and if they save t number of rectangles, then we have the property that t is at least k by 2. From the fact that totally k are killed, so you're distributing k tokens, and each of these rectangles which are receiving token, they can receive at most 2 tokens. So at most k by 2 rectangles, you have to save at least k by 2 rectangles. And that ensure this t by k plus t is 1/3, and that ensures the total loss to be half times 1/3, which is 1/6. Any questions so far? So now we build on this idea of, again, charge distribution further and further. So for example, if I just look at this proof, the loss we had was this factor 2, which was half times 4. So if I have some modified proof for which this property was true, that instead of 4 corners, only 2 corners are charged, then everything will work out as previously, but instead of 4 here, I'll have 2 here, and that will give you 1, and that will give you a factor 1/4 by the same argument. So how to ensure this property, that only 2 corners of a rectangle are charged, not 4 corners? So for that, what we do is we get fences which are more complicated, which have more bends. The reason being, if we look at, let's say, this particular rectangle. Now it can, when this was killed, maybe it will get charged from here, and maybe for some other rectangle was killed for which it could have gotten charged even in this corner. But then again, if this was killed like this, it could have gotten charges from here as well. So I want to ensure that if some rectangle is protected, it should not get charged from the other side. So the longer side is making sure this rectangle is also protected by using more bends. So now the fence is like this, bends, and you protect more rectangles. The right side is also blocked. So you cannot get charge from the right side. You can only get charge from the left side. So only 2 of the corners will get the token, not 4 corners. And that will give you this 4 approximation. Okay. So we build on this again. So now the idea is we want to save as many rectangles as possible. So whenever we are giving token to a rectangle, we want to ensure that it's safe. So let's say in the good case, each rectangle can see. So we proved that each rectangle can see at least 1 rectangle on each of the sides, and that was giving us this 4 approximation. But if, for example, if we know that each rectangle was seeing 2 rectangles on each side, then it is even better. So then, for example, in the one case when there are 2 corners which were seen by the rectangle, then after killing R, actually both this will be protected. So we are actually in the better shape. So having more corners visible is actually better. So using, but it may not be the case always it is true. For example, in this example, for example, it only sees 1 corner, not 2 corners. But then what we do is we still have 2. Now we have, earlier we had 1 token and we're distributing half and half. Now we create 4 tokens, each of size 1/4 for a rectangle, and we distribute 2 tokens to right, 2 tokens to left. And we have something called indirect C. So we distribute the first token to the first directly visible corner, and the second token we kind of pass it along, and we actually go along this line, and the last rectangle hits, and if this last rectangle becomes a red rectangle, we pass it to this, and if it's not a red rectangle, we pass to the other corner. So it's technical, but what we ensure that you can actually ensure that you can distribute 2 tokens for 4 tokens, basically 2 to each side, and you will make sure that whatever rectangles are getting token, they are protected. We will not kill them by fences. So that gives you 3 approximation, because now in the previous proof where we had only half times 2, we'll have now 1/4 times 2, which is half, and that will give this bound to be 2/3, and that will give here 1/3. So that gives you 3 approximation. Now from 3 to 2, it's slightly more complicated, but it is based on the token distribution idea only. Now instead of 2, actually we distribute more and more tokens. So it has a more complicated token distribution strategy, and also now we need more additional properties in this partitioning lemma. The previous partitioning lemma we talked about, which has 20 sides and other stuff, that has only the fence was only 1 line segment. But now what we'll do is we'll ensure the fences have more sides, so 1/epsilon number of sides, and that will need these polygons also to have more complicated number of sides, so maybe 1/epsilon to the power constant, but it's still a constant, and it may not be even horizontally convex, so it can look this kind of weird shape as well. So that's possible. And what now we ensure that whatever rectangle we kill, we can distribute more and more tokens. So now this is what we do is we create some kind of directed graph, and we create some kind of a tree basically, and we ensure that for a cut rectangle, if we take the path from this, either we hit a red rectangle or we hit sufficient number of blue rectangle, at least like say 1/epsilon number of blue rectangles, and we can protect them by fences of size 1/epsilon and then stop. So this will ensure that for each of the killed rectangle, blue rectangle, either there is a corresponding saved red rectangle or we save 1/epsilon number of blue rectangle. So intuitively that gives you 2 plus epsilon approximation. So almost all the blue rectangles are saved, or if you kill lot of blue rectangles, equal number of red rectangles are saved. So that gives you 2 plus epsilon approximation. So any questions so far? Yeah, this last part was technical, but the idea builds on the previous fact that as long as we have some cutting strategy which ensures we have constant number of sides and there are constant partitions, and then this token counting argument says that for each cut rectangle there is a good number of saved rectangle, that ensures this guarantee. So key takeaway is the idea of fence and cutting strategy for the geometric decomposition, which might be useful in other problems, and this token distribution strategy, which might be used in the analysis. Yeah, Sujay, you have a question?
Thanks, Arindam, for the nice talk. Actually, I have a question. So we know that there exists
Yes.
a p-test for this problem. I mean, we don't know the answer, but because there is a q p-test, we know that this is not APX hard. So what is the problem precisely with this strategy? I mean, why it cannot be pushed to 1 plus epsilon?
Okay, so this is a tight example for this problem. Actually, you can, I mean, the way we do the analysis, we are losing half of the rectangles in the beginning. We are only taking red or blue. So in this case, actually, we lose half. In fact, the problem is this charging argument that we are doing, or token distribution. It uses the idea of seeing, which works for rectangles. But if you just have, let's say, axis parallel line segments, so a similar kind of thing, let's say like this. So even in that case, we don't know how to beat factor 2, because this kind of charging ideas will not work, or none of the strategies even work for line segments. Forget about rectangle. So there is already this problem with line segments. I think to go beyond 2, we need some significantly new techniques. At least first we have to understand the line segment, axis parallel line segments, how to resolve them.
But line segment 2 approximation is very trivial, right? It's just 2-dimensional.
That is the best known. So can you get better than 2? Even 1.99, that is not known. And it does not seem like it's easy.
And one additional question. So this strategy will work fine, I guess, also if you have a constant number of orientations. So this is like only 2 orientation.
Okay. That actually, I mean, the DP one will work for sure, but the problem could be with the charging argument. I have to think a bit. Yeah, charging, I'm not sure, but maybe it will work. I
mean, if you have constant number of orientations, then like this cut line, so of course, it's no longer orthogonal cut, but this cut also has like only constant number of orientations.
Right, so as I said, the cutting strategy will work. But the analysis part, the token distribution strategy that we have, that it needs some more work. It's not clear. So the analysis part we have to work out, but the DP will work, the cutting strategy will work. Those two are fine. But whether those cutting strategies produce good cut or not, that the analysis part, it needs some more work.
Okay, thanks.
So I have around 5 minutes more, I guess. So I will just briefly talk about the weighted case. So this does not actually, our technique does not extend to the weighted case, because we crucially use this token distribution idea, which relies on seeing, and it uses the cardinality kind of properties in the analysis. So for this, still the best known approximation is order log n. But I believe our algorithm should give you constant approximation as well, but I don't know the analysis. So we don't know how to do the analysis. So my conjecture is probably even the guillotine cut will give you 2 approximation for MISR, but we don't know how to do it. So briefly, this log n algorithm, it uses a linear program, which is called click constraint LP. So it says that, okay, I create this, I look at the intersection graph, and this says that I want to select maximum weight independent set, xi is one independent set, and for each of the, so xi is the selected rectangles, and for each click, I want at most 1 rectangle to be selected. And that will ensure the independent set property. And this LP has connections with graph theory, and integrality gap of this LP has connection with other problems as well. So this is there's a conjecture actually, which says chromatic number and click number of rectangle intersection graph are constant factor array. If that conjecture is true, it's an existential conjecture, then using this LP, you can actually get constant approximation for weighted MISR. So that's a structural problem for graph theorists. Prove this fact. That so right now we only know it's order omega log omega, but if you improve to order omega, you already get a constant approximation for MISR. Okay, so to conclude, these are the open problems. The first is, of course, p-test for MISR, which will be very interesting. In fact, people believe there should be a p-test for even arbitrary oriented rectangles or polygons as well, because there is a q p-test for those objects. Second is even this next easy question, at least to go beyond our technique, you just get 1.99 approximation for axis parallel line segments. And then the question is second, can we extend our techniques to constant approximation for weighted case? So as I mentioned, the algorithm should be fine. The recursive partitioning should be fine. It's only the analysis part which we could not show. Third, fourth is resolution of this conjecture that chi-g, the chromatic number of rectangular intersection graph, is order omega g. Omega is the clique number of the graph. Then the resolution of Cock-Tardos conjecture and extension to higher dimension. So you can show for d dimension, can you get similar kind of bound? And even for arbitrary line segment, when we have arbitrary orientation, the base known bound is n to the power epsilon. Can we get even polylog n approximation, not poly n, but polylog n approximation for this problem? A constant would be even better, but we know nothing there. So these 7 questions are open problems, interesting open problems in this area. Okay, so I guess that's it. Any other questions?
So the last result uses what? Like separated theorem for string graphs, no? That one.
Yes, yes. Fox and Park, yes. Yeah, actually, I told about arbitrary line segment, but it works for any curve such that each curves intersect with each other constant number of times.
So,
Okay,
Arindam,
so-
I have a question.
Yeah.
Sorry, Arijit, you had a question?
No, please.
Okay. Okay. Although this is not really studied typically in an offline setting, but I was just wondering, because this weighted thing seems quite hard and it has been open for long, is there any study on something like a resource augmentation? So let's say I allow you to stretch the rectangles by...
Yeah.
or
Then you can get beta. Right. So there is a result by Parinya, Andreas Vise, and I think Adamasek, where they showed that if you have rectangles and you can either shrink the rectangles. So in both sides, you have whatever length you have, you reduce by 1 minus epsilon factor. Then the structure of the intersection graph becomes much more simplified, and you can get a constant approximation in that case. It was Peters in that case, and this conjecture is true. Then the chi-g of that change graph is within order of omega g of the original graph.
So this is for weighted as well.
I think for weighted as well. That I'm not sure, but I think for weighted as well. But at least for unweighted, for sure. Yeah.
Sure. Okay. Got it. Thanks.
Any, Urjita, you are asking some question?
So no, we can take the questions offline because we have to set up the next speaker.
Sure.
So thank you, Arindam,
Thanks a lot
for the very nice talk, and everyone for attending this. Okay, Shamantak, so I hand over the thing to you. Okay.
Yeah.
Just one.
Thanks.
Can you just share the slides with me so that I can put it up in the web
With
page?
whom?
Aritra. This is Aritra.
Yeah, I will share with you. Fine.
Just email me and I'll put it.
Yes, really.
Thanks a lot. Nice talk. Thanks.
Thanks a lot.
All right. Okay. So Demalada is here. Can we please make him co-host if he's already Sushmita or Itro, can we make Demallo co-host?
She's doing
Okay, good.
So it's become quite long, no? So yeah.
Yeah.
Did that work?
Yeah.
So Shamantak, could you monitor the chat today as well?
Yeah, sure. I'll do that.
Thanks.
Okay, so it's kind of time by my watch. So let me just welcome you first of all to session 2 of day 2 of RTA 2022. Again, we are delighted to have Demanlo Panigrahi for the second part of his talk. So those of you who could not join yesterday, Demanlo is an associate professor of computer science at Duke University, and he works on a variety of algorithmic problems. And for this talk, he has been talking about some of the recent breakthroughs he have had with his co-authors on the minimum cut problem in graphs. So yesterday we heard about the isolating cut lemma, and today Demanlo is going to give part 2 of his talk. So over to you, Demanlo.
Thank you, Shamantak. As I mentioned yesterday, please stop me at any time and ask questions. I would appreciate that rather than postponing all the questions to the end. Okay, so yesterday I talked about the isolating cuts lemma. So let me quickly recall what that lemma said. So the isolating cuts problem is the following. I give you a graph and a subset of vertices in that graph. And I ask you to find the minimum cuts that separate each individual vertex in this subset from all the other vertices of the subset. So for every vertex little t in this subset capital T, I want the minimum cut that separates little t from the rest of the vertices capital T minus little t. Okay, so that's what the isolating cuts problem is. It's asking for capital T number of the number of cuts it's asking for is the size of the set capital T. And we saw that this problem can be solved using log t calls to any max flow algorithm, which is maybe a little surprising in that it exponentially improves over the naive algorithm that requires t calls. Okay, so what I'll do today is, let's see if this is working. Okay, so yesterday we saw that this lemma gives rise to a new global min cut algorithm. Today we'll see a variety of other uses of this lemma to get a set of new results for other cut problems. So the way I've organized the talk today is I'll sort of quickly go over a few different applications of the isolating cuts lemma in the first half of the talk. I'll go a little fast, but as I said, stop me if you want to. And then in the second half of the talk, I'll sort of dig a little deeper into one particular result or one pair of results on something called a Gomori-Hu tree problem. All right, so the first problem I want to talk about is what's known as the Steiner Min Cut problem. This is pretty similar to global min cut with the following difference. So now I give you a graph and I also give you a subset of vertices that we call terminals. Okay, and what I want you to do is to find the smallest cut that has at least one terminal on both sides of the cut. Okay, so it should split the set of terminals. How it splits the terminals, it doesn't matter. So among all the cuts that do split the terminals, I want you to find the smallest. And as you can see, this actually generalizes the two min cut problems we talked about yesterday, the global min cut problem and the ST min cut problem. So if you choose the two vertices S and T to be in the subset, then the ST min cut problem is the Steiner min cut, is the same as the Steiner min cut. If you chose all your vertices to be in this subset S, then of course all you are asking for is that there's at least one vertex on either side of the cut, which is true of all cuts. So then this is simply the global min cut problem. Okay. So this is a generalization of these two problems. And the interesting thing is that for this problem, even if we allowed randomization, nothing better than the naive algorithm that runs S-1 max flows was known. Okay, so what's the naive algorithm? You fix one of the terminals as a vertex S, and now find ST min cuts of iterating through all the other terminals as T, and then return the smallest of these min cuts. So this was an algorithm we talked about extensively yesterday in the context of global min cuts. You can run exactly the same algorithm for Steiner min cuts, where you restrict your iterations to only the terminals rather than all vertices. But that's pretty much all that was known. Nothing better was known, even if you allowed randomization. Okay. And here's a very simple Steiner min cut algorithm using the isolating cuts lemma. So in particular, the result that we get is that there's a deterministic algorithm for this problem that uses log n max flow calls. Now, I'm not going to give you the deterministic algorithm because it again involves this de-randomization, which is kind of complicated. But here's a simple randomized algorithm. And as I said, there was nothing known even if you allowed randomization. So I do exactly the same as I was doing for global min cut. So I repeat log n times. This repetition, the outer loop, is because I'm searching for the right value of the right number of terminals on the smaller side. And then within that outer loop, I again repeat log n times. This repetition is just to boost the probability of success. And then I sample vertices, but instead of sampling all vertices, now I sample terminals. So I sample terminals at rate 1/2 to the I. The understanding is that if I got the right value of I, then there are 2 to the I terminals on the smaller side of the Steiner Min Cut. And then with constant probability, I will hit exactly one of those terminals in my sampling. Now, if I did that, if I hit exactly one terminal in my sample, then of course, once I run isolating cuts on this sample, I will get back the Steiner Min Cut. Okay, so I return the smallest cut found by the isolating cuts lemma across all these iterations, and that's my Steiner Min Cut. Of course, if the sample doesn't give me any vertex at all, then I don't run isolating cuts at all.
So Dhiman, there is a question. So Venkatesh is asking here, n is the number of terminals or the number of vertices?
Yeah, you can switch, like you can make n the number of terminals. That would also work. I have just used n because the number of vertices is an upper bound on the number of terminals, and for all we know, the number of terminals is let's say a constant fraction of n. Okay, but you can change n to the number of terminals if you want. Okay, and as I said, it's correct because of exactly the same reasons as the global min cut algorithm was correct. I won't go over this. And of course, the running time is dominated by the calls to the isolating cuts lemma. So as we saw yesterday, the isolating cuts lemma can be solved using polylog or just log n calls to max flow. So this gives you overall an algorithm that uses polylog and max flow calls. So this is actually, so I wrote log n in the black box on top. That should actually be polylog n. That's a typo. Okay, there are multiple logs there. Okay, so that gives a new Steiner Min Cut algorithm. This is pretty much an immediate extension of the global min cut algorithm. But you can do a lot more with isolating cuts. So here's a different problem. So this is called the vertex connectivity problem. So a vertex cut is very similar to an edge cut, except that what you are removing from the graph is not a set of edges, but a set of vertices. So a vertex cut is simply a set of vertices whose removal disconnects the graph. Just like an edge cut is a set of edges whose removal disconnects the graph. And the vertex connectivity of a graph is the smallest vertex cut in the graph. Okay, so it's the smallest collection of vertices whose removal disconnects the graph into two isolated components. So the vertex connectivity problem asks you to find a minimum vertex cut, a vertex cut of minimum cardinality. And as an example, here I have a vertex cut that's of size 2, and this happens to be the minimum vertex cut of this particular graph. We typically denote the size of this minimum vertex cut by the letter k, sometimes by kappa. And one thing to note is that there are 3 subsets of vertices we are always going to be dealing with vertex cuts. There's the set of vertices that's actually in the vertex cut. So this is usually called the separator and denoted S. So this is the brown set that I have circled. And then this splits the graph into 2 parts. It could be more than 2 parts, but at least 2 parts. Let's call one of those parts L for left, the other part R for right. Okay, so that's the notation that we use. And this is again just like global min cuts. This is a classic problem in combinatorial optimization, has been studied for many years. The best running time that was known was from about 25 years ago. This is a paper of Hensinger, Rao, and Gabao. And this gives a running time of m times n. Again, m is the number of edges of the graph, n is the number of vertices of the graph. O tilde, as usual, suppresses subpolynomial terms, in particular polylog terms. So that was what was known. We give this new theorem in a work with Jason Lee, Danupan Nanunkai, Thachapal Saranurak, and Sorachai. So we show that there is a deterministic algorithm for the vertex connectivity problem. that uses only polylog and max flow calls. Okay, and if you use current max flow bounds, then this gives a running time of about m to the 4/3, and this unconditionally improves on the previous bound of m times n. Okay, so even if m is like n squared, this still is like m times n to the 2/3 versus m times n earlier. So as you can imagine, it's again going to be using isolating cuts. Every time you see polylog and max flow calls, the right guess is there's isolating cuts involved somehow. But now we will be using the isolating vertex cuts problem. So this is exactly like, yeah.
I have just one clarifying question. So when you are using this black box max flow calls, right? Any algorithm is fine, right? Or does it need to have any? Okay.
Any algorithm is fine.
Okay.
In fact, the flow is not even important. So I'm saying max flow, but from the flow, I will just retrieve an ST min cut. Okay, and this retrieval is kind of trivial. You can use, for example, you can use the residual network to do that.
So yeah. So just one question, Demala. So using this new max flow algorithm, does it imply that now all these algorithms will run in almost linear time?
Yes. So I'll get to that at the end. But yes, short answer is yes.
Okay.
Okay. So what's the isolating vertex cuts problem? So it's exactly like the isolating cuts problem, except that we are dealing with vertex cuts. So I'm again given a graph. I'm given a subset of vertices. And now I want to find for every vertex little t in this subset, a minimum vertex cut that separates little t from the rest of the vertices in T. Okay. And using basically exactly the same techniques as earlier, we can show that the isolating vertex cuts problem can also be solved in log T max flow calls. Okay, so how does that help us? So let's take two different situations. So if the first situation is one where the separator S is actually a small set. Okay, in particular, it's smaller than both L and R. And of course, L and R are interchangeable. It's just left and right. So let's think of R without loss of generality as the larger of the two sets. So R is always larger than L. S in this first case is smaller than L. Okay, let's call that the balanced case. Now, in this case, what we can hope to do is we can hope to sample a vertex subset. Again, I'm using sampling. You can try de-randomizing, but sample a vertex subset such that the following holds: that you sample at least one vertex from R. That part is easy. R is the largest of the three sets. But you sample exactly one vertex from L, and you sample no vertices from S. Okay, and this is possible because S is smaller than L. So if you are sampling at the correct rate with some reasonable probability, you will get this property. For instance, with constant probability, you'll get this property. So once you have such a sample, then you are back to your favorite techniques. So now just use isolating vertex cuts lemma on this sample, and you are done. Of course, there's the other case, the unbalanced case, where the separator is actually larger than the smaller of the two sides. Okay, so L is smaller than R, but S is actually larger than L. In this case, this technique doesn't work anymore because you can't hope to sample a set that misses S but hits L. Okay, like this difference between the sizes of S and L can be arbitrarily large. So in general, you can't hope to get such a sample. So isolating cuts is not very useful here. So for this case, we actually need to devise a completely independent technique that we call kernelization. So this is some version of sparsification, but specifically for vertex cuts. I'm not going to be talking about that. That's the sort of new part in this paper. But what I wanted to illustrate is that at least for one of these two cases, even for the vertex connectivity problem, the isolating cuts lemma is crucial. Okay, so that's one problem. There are other problems where this has been used. So one other problem where this has been used is what's known as connectivity augmentation. So in this problem, I'm given some graph, and I want to find a minimum weight set of edges whose addition makes the graph let's say, tau connected. So when I say that a graph is tau connected, it means that the minimum cut, the value of the global min cut, or the weight of the global min cut becomes tau. Okay, so I want to add a bunch of edges of minimum weight such that the weight of the global min cut of the graph gets raised to tau from whatever it is now. Okay, now of course it's not just raising one cut. Of course there could be cuts that are between the current global min cut and tau. All of those need to be raised to tau in order for the new global min cut to be of value tau. Okay, and this is a well-studied problem. It's also studied because it has connections to something called edge splitting off. That's a primitive that's used frequently in graph algorithms. Now for this, the previous best running time was due to Misr and Karger and used squared time. So they used a version of the recursive contraction algorithm of Karger-Stein to solve this problem. In a result earlier this year, we actually showed that the connectivity augmentation problem can be solved in polylog and max flow calls, again via isolating cuts. It's basically one of the main components of this algorithm is isolating cuts, although there are a few other components that also go into this algorithm. Now, one thing to note here is that unlike in the case of, let's say, Steiner min cuts, there's no reason to believe that a problem like connectivity augmentation actually needs you to run max flows. Okay, so if you might be able to even avoid max flows altogether. Just like in global min cut, this problem also is very related to global min cut. So there's no reason to believe that you need max flows. And in fact, you don't. So in some upcoming work, we show that you can actually solve this problem in near linear time, in O tilde m time. Okay, so this doesn't use isolating cuts. Of course, one restriction or limitation of isolating cuts is that it uses max flows, so it can't go beyond max flow time. Okay, so this uses a very different set of techniques. Not going to be talking about that, but I wanted to mention that this is one problem where you can apply isolating cuts that gives you some new results, but you can do something that's even better. And then isolating cuts has been used by other researchers, for instance, in these two papers by Chekuri and Poinrad and Mukhopadhyay and Nanongkai. And they have extended isolating cuts to things like hypergraphs, symmetric submodular functions, symmetric bisubmodular functions, and so on, with the purpose of using it for things like element connectivity of graphs and hypergraphs. So element connectivity is this sort of hybrid between edge and vertex connectivity, where you partition the vertices into terminals and non-terminals, and the non-terminals operate like edges, the terminals operate like vertices. So it's a bit of a complicated problem, but it has some interesting applications, and you can actually extend isolating cuts to handle these kinds of more general problems. All right, so that brings me to what I'll spend most of today's talk on, and that is about finding multiple minimum cuts. So far we have been focusing on these problems where the goal is to find a single cut. Okay, so whether it was Steiner cut or vertex min cut or global min cut, the goal was to find one minimum cut. But now let's focus on problems where we are required to find multiple cuts. Okay, and in particular, we'll focus on two classic problems. The first is the single source min cuts problem. So you should think back to single source shortest paths, for instance. It's a similar problem for minimum cuts. So here we have a fixed vertex S. This is the source. And our goal is to find ST min cuts for every other vertex T. Okay, so we are actually looking for n-1 cuts rather than just one cut. So that's one problem that we are going to be interested in. Another problem that we are going to be interested in is a richer problem. So here we are not just interested in ST min cuts with a fixed source S, but we are actually interested in ST min cuts for all pairs of vertices S and T. Okay, so we want to find the minimum cuts for all pairs of vertices. Now here's a very simple single source min cuts algorithm. So maybe the first algorithm you would think of. So you have a fixed vertex S. Now I have to find the min cut from S to every other vertex. So what do? I simply iterate over all the other n-1 vertices. And for each such vertex, I find the ST min cut, and I just return all of these ST min cuts. Okay, so clearly, trivially, single source min cuts reduces to using n-1 max flows. Now, interestingly, all pairs min cuts, which does not have this naive reduction, because you're actually, in principle, you're looking for n choose 2 min cuts here. But there's a beautiful result by Gomori and Hu, one of the classic results in combinatorial optimization. They showed 60 years ago that, in fact, the all pairs min cuts problem also reduces to n-1 max flows. Okay, so I won't be giving you the details of how this algorithm works, but if you're interested, it's a beautiful algorithm. You should go and look up. We will come back and talk a little bit about this result, and we will kind of pick something from this result that's going to be useful for us. But these two results basically establish, or the all pairs min cuts result and the simple observation for single source min cuts establishes that these two problems, single source and all pairs min cuts, can be solved using n-1 max flows. Now, the surprising thing is, more than 60 years after Gomori and Hu's work, these remained the fastest algorithm for these two problems. So for both the single source min cuts problem and the all pairs min cuts problem, we had no better algorithms. And this certainly was not due to lack of trying. Faster algorithms were known in pretty much every class of graphs you might be interested in. I've just listed a few of them here, but there are other results that I haven't listed. But for instance, if you restricted yourself to unweighted graphs, there are faster algorithms known: simple graphs, planar graphs, surface embeddable graphs, bounded tree width graphs, etc. So for many different classes of graphs, we knew faster algorithms, including some work I did many years back, but nothing was known in the general case. So if I have a general weighted graph, the only algorithm we knew was the old Gomori and Hu algorithm. And in fact, for single source, it was even more stark in that the only algorithm we knew was this trivial algorithm that iterates over all vertices. Okay. Now, even more surprising, or maybe going one step further, we knew of nothing better, even if we allowed approximation. Okay, so even if we said that, okay, so maybe we don't want the exact all pairs min cuts or the exact single source min cuts, but we want some approximate min cut, even that did not lead to any better algorithms. Okay, of course, the point here being that approximations tend to lead to faster algorithms for many of these problems. For example, for the ST min cut problem, if you allow a 1 plus epsilon approximation, that actually leads to near linear time algorithms that have been known for several years now. Okay, but not for these problems. So the way I want you to think of this is the following structure of problems. So here, as we go down this tree, I'm making the problems more and more specific. So the most general problem is, of course, all pairs min cuts. If I can solve all pairs min cuts, I can answer all the other questions on this slide. Stricter a specialization of all pairs min cuts is the single source min cuts problem. Okay. Now, as I said, for both of these problems, the two problems on top, the best algorithms we knew were running n-1 max flows. Then a further restriction is the Steiner min cut problem. Okay, so of course, if you knew a single source min cut algorithm, you could solve Steiner min cut by simply selecting one of your terminals as the source. For Steiner min cuts, we have a better algorithm that we just discussed. We have an algorithm that runs polylog n max flows rather than n-1 max flows. And then, as we discussed, Steiner min cut is actually a generalization of the global min cut problem and the ST min cut problem. And for the global min cut problem, we already knew a near linear time algorithm. This has been known for many years now. For ST min cut, we did not know this. So we had an algorithm that runs in m plus n raised to 1.5 time. Okay, so this was the state of the art. And by our isolating cuts lemma, we showed an equivalence between the Steiner Min Cut and the ST Min Cut problem. So remember, the isolating cuts lemma was used to solve Steiner Min Cut by running a bunch of ST Min Cuts, polylog ST Min Cut calls, or polylog max flow calls. So there's a polylog equivalence between these two problems. Up to polylog factors, they have the same running time. The rest of the picture was exactly as I've drawn it here. Now, one thing you might wonder looking at this is whether there's also an equivalence between the problems on top. So Gomery, the all pairs min cuts problem and the single source min cuts problem, both of them have the same running time, n-1 max flows. So you might wonder, can I use any single source min cuts algorithm to solve all pairs min cuts, or is the Gomery-Hu algorithm special in some way? So it turns out that these two are in fact also equivalent. So this is new work. So initially this was observed by Abud, Krautgramer, and Tribelsi, and then in a couple of papers we kind of refined this reduction a little bit. So we made the gadget a little weaker than what they had originally devised. But basically the bottom line in these three results is that you can also establish an equivalence up to polylog factors between the single source and the all pairs min cuts problem. So really, it reduces to this one big question: can we solve single source min cuts any faster than the trivial algorithm that runs n-1 max flows? Okay, and this is the question we are going to attack now. Any questions so far? Okay, let's keep going. So before I go further, what I'm going to do is I'm going to talk a little bit. I'm going to take a little bit of a detour, and I'm going to be talking about approximation algorithms. Okay, so remember I said that even if you allow approximations, we didn't know how to go beyond this n-1 max flow algorithm for any of these problems, for either single source or all pairs min cuts. Okay, so approximation didn't seem to help. Even larger approximation factors, things like constant approximations, log approximations, things like this. Okay, so what I'm going to do is now I'm going to allow a 1 plus epsilon approximation. So that's as mild an approximation as you can imagine. And we are going to explore whether this approximation helps us go beyond these n-1 max flow type algorithms.
So quick question before you move on. So for the bottom three, or at least the two leaves at the end, there are algorithms that do not use max flow.
So global min cut does not use max flows. It's in fact faster than max flows. ST min cut is the same as max flows.
Okay, I guess I was wondering whether like the use of max flows for the other one, like the top ones, are sort of crucial. Maybe that's not the point of your like study. Like you do want to sort of reduce it to max flow calls. Or let me ask it in the other direction. Like let's say I give you a black box, like a really fast black box for the Gomery-Hu tree or like the all pairs. Can you use that to find max flows?
So you can find certainly like that. So all pairs min cuts is a more all pairs min cuts is a more general problem than just ST min cut, right?
Yes.
Like from all pairs min cuts, I can retrieve ST min cut.
Right.
I may not be able to retrieve a maximum flow, but in this entire picture, none of these problems is about finding flows. So when I say max flows, it's just because I want to use max flows as a term for ST min cut algorithms.
Okay, just the saturating cut suffices for you.
Yeah. So the usual way that you would find an ST min cut typically would be run a max flow algorithm and then find the saturated cut.
Right, but there are other, like you can use the LP or something like so. That's why the question.
Sure. I mean, if you like want to bypass max flows, everything that I'm saying still holds.
Okay.
Right. Instead of max flows, if you replace that by ST min cuts, everything that I'm saying still holds.
Okay, got it.
Okay. All right. Okay, so as I was saying, so our real focus is on this single source min cuts problem, and we want to do something using approximations. So let's see what changes if you allow approximations. The first thing that changes is that I don't require my max flow algorithms or ST min cut algorithms now become near linear time. Okay, and again, this has been known for several years. So I no longer have this distinction between what I can do in the case of global min cuts and what I can do in the case of ST min cuts. So that's the first thing, first observation. The second observation is that this polylog equivalence between all pairs min cuts and single source min cuts, this equivalence is actually robust to approximation. So if I gave you an approximate single source min cut gadget, then you can actually find an approximate all pairs min cuts solution using polylog calls to this gadget. Okay, so this equivalence is indeed robust to approximation. Unfortunately, the equivalence at the bottom, so remember the equivalence between ST min cuts and Steiner min cuts was via isolating cuts, and isolating cuts is not robust to approximation. So if I, instead of giving you exact max flow calls, if I gave you approximate max flow calls or approximate ST min cut calls, then we don't know how to use those to find an approximate isolating cuts. Okay, so this reduction doesn't quite work in the approximate world, and therefore for Steiner min, even for Steiner min cuts, once you allow approximations, you don't quite get this polylog and max flow running time anymore. Okay, so the point, so when I say you don't get polylog and max flows, what I mean is that you don't get polylog and approximate max flows. Of course, you can ignore approximation and just run polylog and exact max flows. That would still work. But you don't get the added advantage of using approximate max flows, which are faster. Okay, so that's the situation. So as I said, the polylog reduction from all pairs to single source min cuts is robust to approximation. And therefore, the natural question is, can we obtain an efficient algorithm for 1 plus epsilon approximate single source min cuts? If I can do that, then I would solve 1 plus epsilon approximate all pairs min cuts as well. So let's start off with very simple algorithm. Again, maybe the first algorithm you would think of if I asked you this problem. So let's denote the source vertex S. So remember, it's a single source problem. So we are given a source vertex. Now what I do is I iterate over values of K that are powers of 1 plus epsilon from the minimum to the maximum minimum min cut weight that I can potentially see. Okay. So this, of course, the number of iterations is some polynomial in 1 over epsilon times some log factors in the size of the problem. So I iterate over all these possible values of min cuts. Okay, starting with the smallest possible value going up all the way to the largest value. And these iterations are in levels that are sort of multiplicative levels of 1 plus epsilon. And for each of these geometric levels, what I do is I find all the vertices such that the connectivity, the min cut value from S to that vertex is at most K, is at most the level I am at. Okay, suppose I'm able to do that. So if I'm able to do that, then of course, trivially, I have solved the single source min cuts problem. Because remember, I am going at levels, like each level is 1 plus epsilon times the previous level. So that means that for every vertex, if I identify whether its connectivity is below one of these levels or above it, then I would be able to determine the connectivity of every vertex up to a factor of 1 plus epsilon. Okay. So of course, the catch is, how do I run this last step? How do I find all the vertices such that lambda st is at most K? So that's what we call the cut threshold problem. So what's the cut threshold problem again? I'm given some undirected graph. I'm given a source vertex S. I'm also given a value of the threshold K. And I ask you to find all vertices T such that the connectivity between S and T, so the minimum cut between S and T, is of weight at most k. If I can solve this problem, I'm done with 1 plus epsilon approximate single source min cut.
So what kind of runtime are you shooting for solving the cut threshold problem? Like dependent on k or something?
No, so it will be again like polylog calls to max flow.
Okay, I see.
So in the blue box, in the single source min cut problem, I have polylog iterations or maybe even just log iterations.
I see, because you have discretized the weights. Okay.
Yes. So as long as I can solve cut threshold in polylog calls to max flow, I'm good.
Yeah.
Okay, so in fact, that's exactly what our theorem is. So we show that there's an algorithm for the cut threshold.
Sorry, just one more clarification. So at all these levels, I mean, why do you need less than k? Don't you just need between k and let's say like k times 1 plus epsilon? Because you just need for one level, no?
That's right, but think of this as a sieve, right? So as you go up the levels, at some point vertices drop off from this set.
I see.
Wherever it drops off, that's your correct min cut value up to a factor of 1 plus epsilon. Okay.
Yeah.
So our main theorem, this is a follow-up work with Jason Lee from last year. So we show that there's an algorithm for the cut threshold problem using polylog and calls to the isolating cuts lemma. And of course, the isolating cuts lemma in turn uses polylog and calls to max flow. So overall, we are still using polylog calls to max flow. Now, one thing to note is that these are calls to exact max flow. It's not calls to approximate max flow. Okay, so we are still using exact max flow. As I said, isolating cuts lemma cannot handle approximate max flows. But as a consequence of this, we can now solve the 1 plus epsilon all pairs min cuts problem using polylog and max flow calls. So we went from max flow to isolating cuts, from isolating cuts to single source, isolating cuts to cut threshold to single source to all pairs. And we keep incurring polylogs in all of these steps. All right, so let's try and dig a little deeper into this cut threshold problem.
So
Yeah.
what's in the previous slide, what's the dependence on epsilon? Like the number of calls?
Yeah, it's just, I think 1 over epsilon. It's just the number of iterations in this loop.
Okay, so it's not like, not hiding too much.
Yeah, it's just 1 over epsilon. Yeah.
Okay.
So there's no epsilon involved inside the cut threshold problem. Like the cut threshold problem doesn't even have an epsilon. It's only in this outer loop. Okay. All right, so let's see how we can hope to solve the cut threshold problem. So for this, I need to go back to this 60-year-old algorithm of Gomori and Hu. I won't tell you what the algorithm is, but I'll tell you what they came up with using their algorithm. So they came up with this idea of what's called a Gomori-Hu tree. So given any undirected graph, this graph may or may not be weighted. The Gomori-Hu tree of this graph is a weighted tree on the same set of vertices with the following property. If I take any two vertices in this graph, so let's say the vertices S and T that I have shown here. Now, if I look at the tree, I can easily determine the minimum cut between S and T. In particular, it will be the minimum weight edge on the path from S to T because it's a tree. Now, take that minimum cut. In this particular case, it's the edge of weight 2 incident on S. Take that edge. Now that defines a bipartition. If you remove that edge from the tree, that defines a bipartition of the vertices into 2 parts. Take that and put that bipartition, sort of project that bipartition back to your original graph, okay, in the way that I have done here. If you do that, the Gomori-Hu tree property says that what you will get in the original graph is also an ST min cut, and the value of that min cut will be exactly equal to the weight of this edge in the tree. Okay, so the ST min cut in the tree corresponds to an ST min cut in the graph, both in terms of how the vertices are bipartitioned and in terms of what the weight of this cut is. So that's what a Gomory-Hood tree is. Now, why do we want to use this, or how do we want to use this? So let's do the following. So let's say that our threshold K in this, let's take a particular example where in this Gomory-Hood, in this graph, we set a threshold of K equals 2. Okay, so we want to find all the vertices whose connectivity from S is no more than 2. Now, one way of identifying these vertices is the following. Let me start walking outward from S on the Gomory-Hood tree. Whenever I encounter an edge of weight 2 or less, I know that all other vertices on the other side of that edge, all those vertices must have connectivity 2 or less from S. Right? So if I walk outward from S, the two edges that I encounter that are of weight 2 or less are these two edges of weight 1 and 2 in this tree. Then the answer to my cut threshold problem would be exactly the set of vertices that are on the other side of these two edges, 2 and 1. Okay, because their connectivity to S would be less than 2 because they have this edge of weight at most 2 on their path to S. Okay, now of course this is completely useless algorithmically because we certainly don't have this tree in at our disposal. If we did, then we would have already solved the all pairs min cuts problem. But just as a thought experiment, these are the set of vertices that I want to identify. Okay. So any questions about this? This is an important point. In the next 2 slides, I'm going to exploit this.
I still have a little bit of difficulty that when you write these weights 2, 1, 4, 4, 3, why can't this one be distributed across this Gomory-Hood tree?
What do you mean by distributed across?
I mean, why is it the minimum weight age is like centered, like the way you did one here, no? Why can't there be one at some other edge?
There could. Like, it's not necessary that these edges are incident on S. That's not necessary. You're just walking out of S.
Okay.
Wherever you encounter an edge that's 2 or smaller, you say everything, all the entire subtree under that edge are a set of edges, vertices I need to distinguish.
I see. Okay. Okay.
Okay. So it's just coincidence that these edges are incident on S.
Okay. Got it. Thanks.
Okay. So let's set up a little bit of notation. This is the only bit of notation that you're going to see. So let me call a closest vertex to S with this property that lambda, the connectivity is no more than K. Let me call that V. So basically, like pictorially, this is the first vertex you encounter after you cross an edge of value 2 or less. So I've shown this vertex V in this graph. Okay, of course, there's no unique V. There are many candidates for V, but let's take any one such V. Okay. So now let me call the entire subtree that subtended by V, the entire subtree being separated by V from S. Let me call that T sub V. And let me say that the size of this subtree is N sub V. In this particular example, the size of the subtree is 5 vertices. So N sub V would be 5. Okay. Now, remember that this entire subtree must be identified by my algorithm because all of these vertices are going to be in the answer for the cut threshold problem. Now, the key idea is the following. Suppose I sample vertices at rate 1 over N sub V. If I do that, then with constant probability, I'll choose exactly one vertex from this entire subtree T sub V, because T sub V has N sub V vertices. If I sample at rate 1 over N sub V, with constant probability, I'll choose exactly one of these vertices. Now, what is the probability that this specific vertex that I sample is actually the vertex V itself? That probability is about 1 over N sub V. Okay, or constant over N sub V. Okay, so there's constant probability that you choose exactly one vertex. And then given that you have chosen exactly one vertex, what's the chance that you ended up choosing V precisely? That's another 1 over NV. So it's 1 over NV times some constant. So that's the probability with which my sample hits precisely V. Now, if I get such a sample that hits V and nothing else in this subtree T sub V, now what I can do is I can run isolating cuts lemma on this sample. And let's say I dump S into this sample. So I add S to the sample. Now you run isolating cuts lemma. Since V is the only vertex sampled in T sub V, isolating cuts lemma will actually reveal this entire cut T sub V. Okay, because that's the smallest cut that's cutting off V from the rest of the sampled vertices. Okay, so that's the main idea, that we are somehow going to be sampling we are going to be sampling at rate about 1 over n sub V. That will hit V with probability about 1 over n sub V. If it does so, then isolating cuts lemma will give me the answer, will give me entire T sub V's. Okay. Now this should raise
Could you
two questions.
please repeat the isolating lemma? How do we run the isolating lemma? Could you please repeat the step 4?
Okay. So this is a tool that I discussed yesterday. So this tool does the following. If you give it a subset of vertices, then it finds
I understood the I know the isolating cuts, but I just want to know that how step 4 is being enumerated here.
So if once you sample, you have some sampled set of vertices, right? Add S to that sample. So that gives you a set of vertices. On that set of vertices, you run isolating cuts lemma. Like isolating cuts lemma needs a graph and a subset of vertices to run. So the graph, of course, is the original graph, the input graph. The set of vertices on which you are running isolating cuts is the set of sampled vertices plus S.
Okay.
Does that answer your question?
Yeah, thank you.
Okay. All right, so this should raise sort of two red flags. The first is that we don't know the value of n sub V. Of course, this is something that we have encountered a bunch of times, and as usual, this is not the bigger concern. But really the big concern is, are we revealing vertices fast enough? Right? Remember, the probability that I will choose precisely V in my sample is not very high. It's like 1 over the size of a TV, right? It's 1 over n sub V. N sub V can be large. It can be n over 2, for instance. Then this probability is just 2 over n. So we are revealing all these vertices, but with fairly low probability, with just probability 2 over n, if n sub V is n over 2. So is that good enough? Are we revealing vertices fast enough? Okay. So to answer this, let's first look at the overall algorithm. So what's my overall algorithm? So here's the algorithm. I start off with this set of vertices U, which is everything except S. So U will basically be, I will remove every vertex that I have already identified as an answer to the cut threshold problem from U. So U starts off with everything. Every time I realize that some vertex has connectivity less than K from S, I remove it from U. That will be the way the algorithm proceeds. Okay, now I repeat the whole thing polylog n times. This is just to boost sampling, boost probability of success. So ignore this outer loop, it's not so important. In the inner loop, what we are doing is we are again doing these iterations with I from 0 to log n. So again, what am I trying to do? I'm trying to guess the value of n sub V, right? And my guessed value is 2 to the I, okay, in the iteration where I have set I to a particular value. So now within that iteration, what I do is I sample U, all these vertices that I still don't know whether they are less than K or bigger than K. So I sample U at rate 1 over 2 to the I. Okay, this is what I promised to do on my previous slide. I was trying to sample at rate 1 over n sub V. 2 to the I is my guess for the value of n sub v. So I sample at rate 1 over 2 to the I. I obtain this set T. As I promised, I run isolating cuts on T sub T union S. And once the isolating cuts returns a bunch of cuts to me. If any of these cuts are of value less than or equal to K, I simply remove all the vertices that it reveals to have less connectivity than K from S. I remove all these vertices from U. Okay, and I keep doing this polylog n times. I claim that once I've done this polylog n times, with high probability, I have identified all the vertices that had connectivity less than K. Okay, why is that the case? So what I precisely claim is that in expectation, the size of U drops by a factor of 1 minus 1 over O log n in every step. Okay, so if I started off with, so suppose I had to identify a bunch of vertices, 100 vertices. In every step, in expectation, I will identify 100 divided by log n vertices. Okay, so if I am able to do this in expectation, if the number of vertices that are left to identify, if that number keeps dropping by a factor of 1 minus 1 over log n, then of course after polylog n rounds, I'll be done. All the vertices would have been revealed at that point. All right, so what's the proof sketch? So let's look at any one vertex V. Okay, so what does this vertex V do? So as you see in this figure, vertex V reveals n sub V vertices with probability about 1 over n sub V. Okay, so if I think of the expected number of vertices that V reveals, okay, it's kind of revealing n sub V vertices with probability 1 over n sub V. So it's revealing a constant expected number of vertices. Okay. Now, the point is that if you look at any particular vertex now, it can only get revealed log n times because I'm running this for I equals 0 to log n. So every vertex gets revealed at most log n times. And the total number of vertices I am revealing, the expected number of vertices I am revealing with repetition is the total size of U. So that means that overall, I expect to reveal at least 1 over log n of the total number of vertices I had to reveal. Okay, so if that was a little sort of hand wavy, then that's okay. So we don't need to, you don't need that for the remaining few slides. But if you are interested, I encourage you to take a look at the paper. It's kind of a classic counting argument. Okay. So given this, now what do we have? So we now have a polylog n max flow based algorithm for all of these problems. So remember, this algorithm actually solves single source min cuts. And there's this polylog equivalence between single source and all pairs min cuts, which means now all of these problems, all pairs, single source, and Steiner min cuts, has this algorithm that uses polylog n max flows. The only catch, as I said,
sorry.
Yeah,
I have one doubt. Maybe I missed something. So when you are using isolating cuts for this problem, don't you need that S is actually that singleton on one side of the cut, specifically S?
No, not S. So V, this, so if my sample had this property, that vertex V is the only vertex in the yellow part of the cut that got sampled.
Yeah.
Then, and all the other vertices, including S, are on the other side. So now when I run isolating cuts,
okay, then you are
V
good.
is one of the candidate vertices in this set. So the isolating cut for V will reveal this yellow cut.
Yeah. Okay. Yeah, thanks.
Okay. All right. So at this point, we have this algorithm that uses polylog n exact max flows. Now, of course, there's this catch. It's still using exact max flows, whereas we are finding an approximation, like it's revealing an approximate solution. So can I actually use approximate max flows? seems difficult because isolating cuts does not extend to approximate max flows. But we did manage to figure out a workaround. So in some very recent work with Jason Lee, Danupon Nanonkai, and Tachapal Saranurak, we showed that what we can do is we can actually retrieve isolating cuts, not with arbitrary approximate max flows, but with something that we called fair max flows, okay, or fair min cuts. And this fairness property is kind of technical, but this is a restriction on approximate max flows and min cuts. It's some subset of max flows and min cuts that we denote as fair. And we show that this extra restriction of fairness does not affect the running time. So a fair max flow or a fair min cut can also be computed in near linear time. Okay. And the advantage of fair flows and cuts is that they can now be used in the isolating cuts framework. Okay, and using this, we actually reduce the running time of all of these problems, the approximation version of all of these problems, to near linear. Okay, so the last couple of slides is about the exact problem. So let's go back to this exact single source and all pairs problem. So there we are still stuck at n-1 max flows, as we discussed earlier. So how can we improve this? So again, in very recent work, we managed to improve this. In particular, we show that there is an algorithm for the Gomory-Hood tree problem. So it constructs a Gomory-Hood tree, which thereby solving both all pairs min cuts and single source min cuts. So there's an algorithm for this problem that runs in O tilde n squared time. Okay, so remember, the previous solutions were all using n max flows. So n max flows is certainly at least n times m. Max flows cannot run faster than m. So this is significantly better than that. And we show this by solving single source min cuts in this time and invoking the reduction between single source and all pairs min cuts. Okay. Now I want to mention that we actually believe that we can actually do this in max flow time. We don't need n squared. But we are still verifying some details in the max flow algorithm. That's a lot more complicated. The n squared algorithm is already on archive. Okay, so let me give you a very brief sketch in the 2 or 3 minutes I have left of how this algorithm works. So let's go back to this sort of 1 plus epsilon approximate single source min cut algorithm. So what were we doing? We were setting these sort of geometric levels at powers of 1 plus epsilon, and we were using a sieve. At each level, we were solving cut threshold. So this allows us, using just this, the fact that we can solve cut threshold, this allows us to partition the vertices into these blocks where we have figured out all the vertices whose connectivity is between 2 of these levels. So between, let's say, 1 plus epsilon to the I and 1 plus epsilon to the I plus 1. Now what we do basically is we try to solve this problem where we are given a set of vertices such that their connectivity from this source S is between K and 1 plus epsilon K. Given such a set of vertices, we want to find the precise connectivity values. Okay, if we can do this, then we can plug that into the blue box and we would be done. Okay, so that's our goal. I'm given a bunch of vertices. I know all their connectivities are between K and 1 plus epsilon K. Can I find their connectivity from S? So this algorithm has 3 steps. I'll go briefly over all the 3. So the first step is to find a bunch of edge disjoint Steiner trees, Steiner with T as terminals. Okay. So these are things we call guide trees. And for those of you familiar with packing, so this is a fractional packing algorithm. Okay, what's the key property? So note that the min cuts that we are after are a value between K and 1 plus epsilon K. Now, if we pack a bunch of edge disjoint Steiner trees, then what will happen is that this min cut in expectation in any one of these trees, if I randomly chose one of these trees, then any such min cut can only have 1 plus epsilon edges in such a tree, right? Because the min cut doesn't have more than 1 plus epsilon k edges, and I have k such trees, and these are edge disjoint. So in any one of these trees randomly chosen, I only expect to see about 1 plus epsilon edges from the cut, right? From the cuts that I am after. So that's the key property of these trees. How do we come up with these trees? Well, this requires some work. So we use a bunch of techniques. We first do sparsification. We then use something called the multiplicative weights update method, which many of you might be familiar with. And then the multiplicative weights update requires a gadget. So this gadget problem, we need to use a Steiner tree algorithm. We use a fast algorithm due to Kurt-Malone. Okay. So, but the bottom line is that we pack a bunch of trees with the property that if I choose a random tree, I don't expect my min cuts to have too many edges in that tree, just about 1 plus epsilon edges. So next I sample log n trees from this packing. Okay, now for each of these trees, the third step is the following. For each such tree, we find the minimum ST cut that has, let's say, at most 4 edges in any of the sample trees. Okay, and by the property that in expectation I only expect to see 1 plus epsilon edges, that means that if I can find the minimum cut with only 4 edges in this tree, I would be able, that would reveal the actual minimum ST cut. Okay, and so the key property here is that an ST min cut is revealed in this step because the ST min cut satisfies this property that it's sparse in the tree. It has very few edges. Okay, and what the main ingredients in the second part are the isolating cuts lemma, particularly the cut threshold problem, and something called centroid decomposition that allows us to run some recursive algorithms. Okay, and in terms of running time, the first step takes n squared time because the sparsifier contains about O tilde n edges, and we have O tilde n iterations of multiplicative weights update. The second step is just dominated by isolating cuts, so that just takes polylog max flows. And we believe the first step we can actually make that polylog max flows as well, but it's much more complicated than the algorithm I described. Okay, so that's the theorem. On unweighted graphs, we can already show that you can do it in polylog and max flows already in the paper that we have posted. And as I think Saket mentioned a little while back, so a paper was posted yesterday that claims an exact max flow algorithm that runs in almost linear time. So if everything checks out, both our speeding up of Gomori-Hu and this paper that was posted, then we would basically at this point have solved everything that I talked about, all the problems I talked about in almost linear time. So we would have really traversed a long journey. Okay, and with that, I want to end. I'll just put this slide up for students who might be interested in new problems. So basically, I'm saying, can you do anything for directed graphs? None of this works for directed graphs for fairly fundamental reasons. Can you do anything at all? Thank you very much.
Okay. Thanks, Demalya. So I will clap on the behalf of everyone. Any questions? Okay, I have like a kind of a high level question. So do you feel that the isolating cuts lemma could be useful, like, I mean, I don't know, either to, let's say in the regime of approximation algorithm, so like either to speed up some existing approximation algorithm or maybe even to break some of the open questions?
So I guess the question is what kind of question, like what kind of problem? So at its heart, what the isolating cuts lemma needs is submodularity and symmetry.
Yeah.
It's really not. It's not really a property of graphs in an abstract sense. So if you have a symmetric and submodular function, then it's a way of minimizing that function.
Right.
Now, the question is, what kind of other situations admit symmetry and submodularity? So some of the other sort of classic examples are things like hypergraphs and so on. But it's possible that there are other situations where you also have symmetry and submodularity, in which case the isolating cuts lemma or an appropriate form of the isolating cuts lemma would still be correct.
But it's mostly to speed up algorithms, I guess, right? Or could it potentially improve approximation factors as well?
That's kind of hard to guess, right? Like, so this distinction is like at a structural level, this distinction between what's useful for speeding up algorithms and what's useful for improving approximation is difficult to make, right? So, for example, all these like new TSP algorithms rely a lot on like cut structure, and in particular cut structure that's polynomial time solvable. So yeah, so that distinction, I'm a little hesitant to make that distinction.
Okay. Any other final questions, thoughts?
So I just had one question there, Malya. So like one of the things which like all these classical polytime algorithms has recently used is this expander decomposition, right?
Yeah.
Is there a good literature to read if I really don't care about, say, very efficient computation, but just a good algorithm to understand how it is used or what it is? Like, is there some decent literature for that?
So I guess the sort of most basic paper for just the idea of why there should be expanded decompositions is this thing called cut matching games. I don't know if you have seen that. This is a paper by Khandekar, Rao, and Vazirani. So they don't even talk about expanded decomposition in the paper, but they talk about this thing called cut matching games that are useful for things like sparsest cuts.
Okay.
But it's like that's where the whole idea of expanded decomposition comes from.
I see.
Now, if so you can, like, in hindsight now you can make the connection. It's pretty clear.
Okay.
So that I would say that's the cleanest sort of first paper to read.
Okay. Okay. Thanks.
Sure.
Okay, so if there are no further questions, then let's thank Malya for the great talks, like the couple of talks, and thanks once again for staying up past midnight. So
thanks for inviting me and hosting me and coming to my talks. Thanks to all of you. Thank you.
Okay. Hopefully we can host you some next time in person. Thanks, Malya.
I would love to. Thank you.
Thank you.
So I would like to thank, we have ended the morning session with 2 talks, 2 parts. And I'd like to thank all the speakers as well as all the chairs for doing such a wonderful job, and all the participants for showing up in large numbers. So I guess we'll see you in the next post-lunch session, right? Thank you.